Okay, so one byproduct of running the extra is that you can compute the shortest path tree, right? You can compute the shortest path from S to all the vertices in the graph, and it forms a tree. And of course, how do we do it? Well, we need to do some labeling and remembering when we do the computation. So the idea is that for every vertex, we're going to maintain a previous pointer, which points to the previous vertex where the shortest path came from. And we need to maintain it every time we do a decrease operation. Decrease key operation, we just maintain point U to the vertex V that caused the candidate value to decrease. As such, the last decrease key that fixed the value of the vertex would also set its predecessor to be the right vertex, right? And clearly this creates a tree. Why does it create a tree? Well, if it wasn't a tree, if we had loops, then we would have loop in the shortest path, which is of course not possible. So this is a tree and everything goes back to S, so it is a tree, it's not a forest. Okay, so that is that. I guess the only other important thing to observe, of course, that we need to initialize it. The previous vertices to null to all the vertices before we start the execution. The running time is clearly unaffected by this modification, right? It's just a tiny tiddling. One still need to prove that what we get is this reverse tree, right? Edges now go from the vertices on the tree back to S. So we need to prove that this indeed encodes all the paths in the shortest path, right? So what is the shortest path now? If you have a vertex, you just go on the edges of this reverse tree back to the source, and this is going to be the reverse of the shortest path from S to the vertex V you want. And the proof of that is boring induction on the size X, as we already done before. Let's not bore ourselves to any further. Okay. How about the other direction, right? We want to find the shortest path from all the vertices on the graph to V, right? The reverse problem. So all you have to do is just you reverse the graph, right? You compute the reverse graph and you compute shortest path in the reverse graph. We already did it when we spoke about DFS and strong connected component. We use this reverse idea quite a lot. So just run the extra on the reverse graph and you get it. So that's also easy and nifty.